Hello students, welcome back. In the first video, we talked about what it means by sampling distribution, and we went through a couple of examples of sampling distribution of sample means. Once in a simulated experiments problem, and then a couple more times in visualization problems. Well, here they don't really look like normal, but if I increase the number of repetitions, you can clearly see the normal pattern forming for the sum and also for the means. And this one too. Right now, with just 100 repetitions, you don't see any pattern formation, but with 1 million repetition, you're going to see a nice normal picture developing. So what's the conclusion here? Sampling distribution of sample means follows, well, these kind of properties. Mean is mean, that stays the same always, and it hovers around 3.5 no matter how many times I run it. As for standard deviation, the individual follows this standard deviation, and the standard deviation of sample mean follow this quantity given by sigma over square root of n. In this case, simulated 20 rows, so n value is 20, and this quantity hovers around sigma over square root of n. Now, we're going to put those two together, those quantities and also the normal picture. If we do that, we end up with this conclusion. Let x be a random variable with mean mu and the standard deviation sigma. And then we repeat it independently for sufficiently many times. If we do that and take the average, that will follow more or less, approximately, a normal distribution of mean mu and the standard deviation of sigma over square root of n. This result is called the central limit theorem, and this is really the fundamental theorem of statistics. Extremely important, arguably the most important, but it's too hard. It's definitely out of undergraduate level, certainly not in 1000 level. Still, that does not mean we cannot use any part of this. We will use it. How are you going to use it? Well, the new standard deviation of this sampling distribution of sample means is sigma over square root of n, that is, old standard deviation over square root of n. That's a bit too confusing. New standard deviation is old standard deviation over square root of n. New standard deviation, old standard deviation. The standard deviation of sampling distribution of sample means is the standard deviation of the individual over square root of n. Oh, too confusing. That's why people created another name, standard error. And this quantity, sigma over square root of n, will be called the standard error, SE. Let me expand the font a little bit. So for sample means, SE, the standard error, is sigma over square root of n. This sigma standard deviation is for individuals. Furthermore, let's make some further observation. If n is equal to 1, then SE is nothing more than, let's see, sigma over square root of n, right? But n is 1, so what do you get? Just sigma. So what does that mean? You don't really have to use any formula with sigma at all. If you just use SE as sigma over square root of n, and then if you have an individual, then consider it as a sample of size 1. You see? Individual is the sample of size 1. So this formula, SE formula, always works. Also, another thing, this formula, z equals x minus mu over SE, is very, very important, but there are too many versions of it. X bar minus mu over SC, here we go, and also sometimes X bar minus X over SC, X minus X bar over SC, mu minus X bar equals over SC. There are too many versions. Too confusing as a matter of fact. Much better version is this. N minus center over SE. And of course, what do you mean by N? What do you mean by center? You need a picture to go with it. So draw a picture first, and then use this, N minus center over SE. This one is far more useful. Remember this expression. And then as for standard error for individual is becoming the same as just standard deviation, old one. Yeah, that's rather trivial, so I'm not going to emphasize too much. But this one is really important. N minus center over SC. Now let me emphasize that in bold and also in red. And let me call it the formula number 1 for the entire course. Alright, that's where I'm going to stop, and I'm going to talk about this example in a separate video because it's going to be a bit too hard. So I'm going to stop here.